The final chapter that we will cover is Alice chapter 8, Lists and Arrays. The lists and arrays are basic data structures. If you continue in programming, you'll learn about a whole bunch of different types of data structures. There are arrays, lists, trees, heaps, all sorts of things, self-balancing trees. And they're all very interesting, but unfortunately we don't have time to cover all of them. So we'll cover the two basic ones, which Alice has native support for. The most basic data structure is the array. Recall that I've described in the past variables, parameters, and properties as little spaces in memory that store data. An array is just a bunch of those little spaces all in a row that are indexed. So generally you refer to individual items as an array as array name subscript 0. Subscript in programming is written as a number in these brackets. And then the sixth element is array name subscript 5, and so on. So it's a little bit odd in most programming languages, but you get used to it quickly. The first element of an array is subscripted 0, meaning that the second element of the array is subscripted 1, and so on. The main downside of arrays is that you generally can't make them bigger or smaller without potentially having to spend a lot of computer time shifting data from one little space to another. So, if you want to make an array bigger, the computer has to allocate a larger space for the array and then copy everything from the smaller array to the bigger array. And so that can take a lot of time. If you delete something from an array, there is a hole where the data used to be. So if you want to make an array smaller by deleting something out of the middle of it, you have to shift everything over by 1 in order to cover up the hole. And then you have to mark that the array is smaller. So there are several downsides to arrays, but the upside is accessing everything in an array in order is extremely fast. Computers are built in many ways to go over every element of an array in order and do something to it very quickly. So that's one big advantage of them, the fact that and it has to do with the fact that all of the data is together. So your homework is over lists, not arrays, because Alice has better support for arrays. But for completeness, I do want to show you some information about arrays, just so you know how they are and how they work, and also what an algorithm that works with an array might look like. So let's look at tutorial 8D. I've got tutorial 8D in Alice right here. And so let's take a look at it. Before I run this world, it's got a whole bunch of ballerinas. And what this is going to do is it's going to sort the ballerinas by height. So the smallest ballerina is going to be here and the largest ballerina is going to be there. And what you will see is an algorithm running which sorts the ballerinas by height. So the world all runs in one method, world.myFirstMethod. And so first we have array.bubblesort. And we loop from 0 up to, but not including the array size, incrementing by 1. And then you have the value at array index, say, value at array index as a string, value at array index, say, subject of the array's index height as a string. And so what this is going to do is each ballerina is going to say how tall she is, and then put her arms down. and then they're going to take a bow. So the only thing that I don't care about this code here, it's great if you understand it, but what I want to focus on is bubble sort. So the object array, and don't be confused, the object array is not an array, it's an object. I know that's kind of weird. Has the method bubble sort, which gets called. And bubble sort is an old, well-known sorting algorithm. It sorts numbers, or anything else, in order. So, while this changed parameter is true, there's a variable here, a Boolean variable, which is initially set to true. And so there's an outer loop here that says while changed is true, set change to false. So change it, make it so that it's false. And then execute this loop. And this loop loops up from 0 to the array size -1. Why -1? Well, you'll see. Recall that the last element of an array is going to be the array size -1 because we start at 0. So the last element in an array is going to have the index of how big the array is, -1. But this is not including that index, so it goes all the way up to the next to last index. And what's this loop do? Well, it executes this if statement here. So it calls a function here. If the value at array index is smaller than the value at array index plus 1, so it compares the current index in the loop with the one following it. Okay, so that's why we don't include the very last element, because if we try to do this with the very last element, there would be no element past it, so we can only go to the next to last element. So that answers that question. If it's smaller, then we swap them. We swap array index and array index plus 1. Now what's the swap method like? Well, swap method is here, and it's basically the swap method that we saw earlier in the lecture where I went through Dijkstra's algorithm, lecture for chapter 5. We have a temporary variable, temp set to the value at array A, which is a number, so A is a number, a parameter. Set array A to the value at array B, and then set array B to the value at temp. So it's exactly the same swapping algorithm you saw before. So there's not much to talk about there. If this is confusing, just look at the thing where we had the bunny give the greatest common divisor of two numbers. So we swap them, and we set this changed parameter to true. And so then, if anything gets swapped, the changed parameter is set to true. So this is going to loop. This loop is going to go through this loop. This loop is going to go through the entire array, and whenever it sees two things that are out of order, it swaps them. And then, if it swapped anything when it went through the array, it sets this change parameter back to true so that it loops again from the beginning. So why is this going to stop? Well, assuming that this method of swapping everything that's out of order is eventually going to sort the array, and it is, eventually the array will be in order, and this if statement will never get executed. These two lines will never get executed. This is only executed if two things are out of order. If nothing is out of order, then this never gets executed. So changed never gets set back to true after it was set to false here. And so this loop ends. And so these slides just go through bubble sort. We went through all of this, the first three, and so I'll just comment on a little bit about what bubble sort is. Exactly. Bubble sort is the best sorting algorithm you should never use. And that is a good statement to carry with you if you do go into programming. Never use anything like bubble sort. Bubble sort is the silliest named one. Some other bad ones are insertion sort. Insertion sort, selection sort is another bad one. There are a whole bunch of bad sorting algorithms that are all kind of similar to each other, and basically just never use them. Sorting algorithms are some of the first algorithms early programmers invented, because early computers were used to do business applications, including sorting things. New sorting algorithms are still being developed today because computers still have to sort data quite a bit. And it's a basic thing that's used in a whole bunch of different applications. I mean, you can probably think about cases where sorting is important. New algorithms are still being developed today, but we have good ones, so the rate of development has slowed. So some popular good sorting algorithms are radix sort, quicksort, merge sort, and heap sort. Just look up those in any computer science textbook if you're more interested in sorting. I just want to mention that bubble sort is bad and you shouldn't use it. But it is simple, and that has some definite advantages for demonstrating a simple algorithm that does something useful. So let's think a little more about this code here. Why is this method of swapping anything that's out of order eventually going to work? Well, if you go through and you swap everything that's out of order, then those two things that you swap each move in the direction of where they're supposed to go in the list. So if these two are out of order, well, okay, that's not necessarily true. So we can't make that argument. So actually proving that this works is going to take a little bit of thought. Because, for instance, these two can get swapped, and that one's going in the right direction, but this one isn't because there's a smaller one over here, and so eventually that one's going to have to go the other way. So, okay, so let's focus on the smallest one. Obviously, there is at least one smallest element in an array that you're sorting, so one of these things has to be the smallest or one of the smallest. Every time it gets swapped, it's moving in the direction that it should go. So you go through here and you reach the smallest one. Well, it's going to get swapped with whatever is before it. And as you continue doing this, it's going to get closer and closer and closer to the beginning of the array. And then it'll never get swapped again, because the thing in front of it is never going to be smaller than it, because it's the smallest. And so then you can look at the next smallest one. After this is over here, and we know it will eventually if we go through this looping where we swap everything that's out of order enough, then the next smallest one is always going to move in the right direction. Because there's the only thing that's smaller than it, the only thing that could swap it out of order is already at the beginning of the array. It's in its proper place. And so it will never need to be swapped again. And then you can go on to the next smallest array and so on. This is called an inductive proof. And so eventually it's going to be sorted. Now you might think, oh, it's obvious, you know, we're swapping everything that's out of order, eventually it's going to work. But you do need to kind of think about it. It's not as obvious as it might seem at first glance. So let's look at it in action. This will be cool to watch. So it's actually sorting them from tallest to shortest, but the same argument holds. Alright, so they all say their names and everything. Oh, and then they take a bow. Alright, so this animation was kind of jumpy. So I'm going to show you again and try to follow the flow of the code. Try to follow it. It goes through it this way and it swaps any two things that are out of order. Try to follow it doing that and see what happens. And I'm going to try to do something on my computer to make it go a little smoother. But if it doesn't, just again, watch again and try to follow along with it. So see, you can definitely see as it travels through the array. At the end it starts to get harder because there are so many things that are in order it's not swapping too much. But you can definitely see. And I'm not going to have them do this again. Alright, so that's how it looks. And so now I'm just going to leave you. We're done with the ballerina, with the 16 ballerinas, but I'm going to leave you with a few brain teasers. And I'm going to go through them, but just try to answer these questions yourself before hearing the answers. What happens if you don't set changed to true inside the inner loop? So we've got our inner loop here. And we set changed to false here. And we set changed back to true here. It's right there, and for some reason I'm having trouble moving it with my mouse. Okay. Changed set value to true. So we set change to true, and let's say we don't do that. Let's say we comment it out. Let's say we don't set change to true inside of the loop. What's going to happen? Think about it. Pause it here. Think about that. Try to and tell me what you think is going to happen if we just take this line of code completely out. Yes, it's not going to work, but how exactly is it going to fail? Alright, so the way it's going to fail is that it's only going to go through this loop once. So I'll show you. We can disable this line and play it and see what happens. Alright, so it thinks it's it ended. It's going through their names and everything. But the list isn't sorted. But the algorithm thinks it's sorted because what this line does is tell this outer loop here, hey, you've got to go through the loop again. The list might not be sorted yet. So if we take that line out, the list probably won't get completely sorted. What happens if you don't set change to false inside the outer loop? So what happens if we take this line and disable it. Think about it. Pause it here, think about it. Alright, thing that's going to happen if you take this line out, and I'm not going to show you, because what would happen is that the loop, this would continue forever. The algorithm would never stop. Because until changed is set to false, until this condition, while changed, is not true, so until this Boolean variable here is false, the algorithm is going to continue looping. It's going to go through, it's going to continue this outer loop forever, so it's going to continue doing this inner loop forever. So that's what's going to happen if you set change to false. The outer loop will never stop. And that's a bug. If the code never stops, it's typically a bug. What happens if you don't swap unordered pairs of elements inside the inner loop? So what happens if you take this line out? Well, pause it. Again, what's going to happen is it's going to keep going forever. And in this case, what's going to happen? Well, okay, it will continue going forever unless the list was already sorted. So if it's already sorted, then the code will work fine. If it's not already sorted, then the outer loop is going to start. It's going to set change to false. This inner loop is going to run. It's going to check and see that it needs to swap stuff, but it's not going to actually swap them. Then it's going to set change to true, so it's saying, okay, outer loop, you need to continue going. It's going to go through the inner loop again. Because nothing changed, it's going to find that same pair of ballerinas that's out of order. And again, it's not going to swap them because we took that line of code out. Again, it's going to set change to true. And so the code will continue looping, doing nothing. So it's not very interesting to watch. The code is looping. The ballerinas will never say their names because bubble sort will never end. And that's all that's going to happen if you do that. What happens if you change the condition on the outer loop from while changed is true to while changed is false? This is the easiest one. Instead of changed, say not changed. What's going to happen? Pause it. What's going to happen is the algorithm will immediately terminate. It won't sort the ballerinas. It'll just return and say, okay, I sorted them, when it's actually done nothing. Because changed is true. Changed starts as true. And so if changed, so this loop is going to, the first line of code is while not changed. This is false when it starts. So is not changed true? Well, changed is true, so not changed is false. So I'm not going to execute this. And because this is the outer loop, that means it's not going to execute any of this. And so if you play it, the ballerinas are just going to start saying their names immediately. So again, they're not sorted, and the algorithm is stopping, but this time it doesn't even go through the loop once. So that's the end to our brain teasers. So let's move on to the next topic, which is lists. Lists are more complicated than arrays, but we're going to talk about them more because they're more supported by Alice. Now I say they're more complicated. They're more complicated in the computer, but they're easier to use than arrays. and Alice supports them better than arrays, so your homework is going to focus on lists. You can add and delete elements from a list during the execution of a program. And instead, the way they're implemented inside the computer is each element of the list contains a little cubbyhole for whatever data is in that item in the list. So read element as item contains the data for that item in the list, and it contains another little cubbyhole with an address in memory to the next element. So if you want to change the size of the list during the execution, you just add another link and put it in there. And so this makes inserting and deleting things from an array more efficient than it would be to insert and delete things from an array. But you're not gonna change. In your homework, you don't have to worry about that. You're not gonna add or delete stuff from a list while the program's running. You're just going to take a list, you're going to make a list before the start of the program and then loop based on the list. And that's essentially all you're going to do for the homework. The homework is not that hard. It's not as hard as the homework for Chapter 5, certainly. What you're going to do is you're going to make a list, and then you're going to use one or more of these loops. These are list loops. They are special loops that Alice provides. This one, the top one, corresponds to something that you would use in real programming more than this one would. This one is more, for the theatrical aspect of Alice, because you can do more than one thing at a time. And what these loops do is exactly what it looks like. For everything in the list, for all your list, one item from your list at a time, go through and do something. And critical thing here, inside the loop, you use item from your list to refer to each item in the list. So you're going through, and every time you have an item in the list, and you're going through and you're going to do something for every item in the list. So think of item from your list as like X. It's a variable referring to an item in the list. So it's a variable, and its value changes every iteration of the loop. So basically, think about how you would, this is kind of a silly example, but think about what you would do if you had a grocery list and you went to the store. You would say, okay, for each item on my list, I'm going to take it off the shelf and I'm going to put it in the cart. And let's assume that this is a supermarket where everything is on the same shelf and they're all right next to each other. Just don't think about the analogy too much. Okay, for every item on my list, I'm going to take it off of the shelf and I'm going to put it in my cart. All right, for grapes, I'm going to take them off the shelf and put them in my cart. For a can of beans, I'm going to take it off the shelf and I'm going to put it in my cart. For a gallon of milk, I'm going to take it off the shelf, put it in my cart. So on and so on and so on. So if you wrote an algorithm for this, it would look like this. So you have a list, grocery list, equals beans, milk, grapes, bananas, pizza. Okay. For all grocery lists, this is how it would look in Alice. One item from grocery list at a time. take item from grocery list off the shelf, put item from grocery list in the cart. So one very important thing to note here is I am not referring, inside of this loop, I am not referring to beans, milk, grapes, bananas, or pizza. I'm saying take the item from the grocery list off the cart and put the item from the grocery list in the off the shelf in the cart. Sorry. Take the item from grocery list off the shelf, put the item from grocery list in the cart. So the list is doing the work of giving me the exact things I need to operate on inside of the loop. So this stands in. This reference here stands in for the individual items in the list. So think about it. That is a critical insight that a lot of students miss when they're doing the homework for this chapter. So make sure that you do not refer to the name to an item from the list by name inside of the loop. That defeats the purpose. The whole point of this list, of using this list, is so that you can refer generically to every item in the list. So I mean, look at this. If you didn't have a list, a grocery list, and you were trying to animate this in Alice, you could say, take beans off the shelf, put beans in the cart. Take milk off the shelf, put milk in the cart. Take bananas off the shelf, and you get the idea. That's how you would do it without a list. So if you do have a list, you don't need to refer to beans, milk, grapes, bananas, or pizza inside of your list loop at all, ever. There might be some cases later in advanced programming where for some reason you do need to refer to an item from the list by name. Maybe because you need to special case it. You might need to say, okay, if the item from the list is bananas, then I don't need to just put them in the cart, I need to put them in a bag first, for example. But in your homework for this class, in this class, you will never, ever need to refer to an object in the list, an item in the list, by name. You use this variable here. This is a variable. It's a variable that exists. It's a special variable. The loop instruction creates it for you. You will use this variable to stand in for the actual items in the list. Okay, so that covers that correct usage of lists thing there. Now, you can have a list of any type of variable. I'm going to go over how to create a list now. They're just another type of variable, and you can have a list of any type of variable. Can you have a list of lists? Well, in normal programming, yes. In Alice, you're not going to do it, at least. What we're going to be working with are lists of objects. So if you recall, an object in Alice is something like a bunny, or Alice Little, or an astronaut, something like that. And that's what we're going to have in our lists. So here's an example that we'll do. I'll create an object, a list of jumpers, and then I'm going to make each of them jump one at a time. For all jumpers, one item from jumpers at a time. Move up 5 meters, move down 5 meters. So let's go ahead and do that. So I'm going to open my triple jump world right here, and I'm going to need to make a generic jump method first. And if you do the tutorials, you'll see how to make generic methods. Generally, you have to make them as methods of the world. You have to make them take an object parameter. Oh, and I clicked variable instead of parameter. You need to make them take an object parameter. I'll call him jumper. And then you say jumper move up 1 meter. And I'm not going to make a parameter. I could make another parameter for how high to jump, but I'm not going to bother. Jumper move down 1 meter. So this is something that can make anything jump. You say, okay, make who jump? Well, make Alice jump. So put these in here. So now if we want to make Alice jump, we can call world.jump, and we can pass them Alice. And so now Alice is going to jump just like she did before. So that's good, that's useful, because now the reason we needed this is because we're going to have a loop, and that loop is going to make a whole bunch of things jump, but that loop is not going to be able to call methods of Cheshire Cat, Alice, or the White Rabbit, because that would require referring to the Cheshire Cat, Alice Little, or the White Rabbit by name, which we just talked about you can't do, or you're not supposed to do. So the way this code is going to work is we're going to take our for all in order thing down here, and oops, we didn't make a list yet. So to make a list, you go to the world. This list is going to be a property of the world. You could also create a new variable right here to make the list, but I'm going to make it a property of the world. And this list we will call jumpers. And the type is going to be list of objects. So once I check this make a list thing here, now it says, okay, it gives me this box here where I can add items to the list. So, okay, add an item, the Cheshire Cat. Next item, Alice. Item after that, White Rabbit. So now I've got my list of jumpers. And so I can click OK now. And you can see that you've got a list right here. So now I can say for all in order, and I select world.jumpers. For all world.jumpers, one item from jumpers at a time. And now I can say, I can bring in drag jump here. And the jumper is going to be the item from the jumpers. So what does this do? Makes each of them jump one at a time. So I didn't actually need to make this world.jump method because I could just say, instead of calling the world.jump method, I could have just said item from jumpers move up and then item from jumpers move down. That would have worked just as well. And see? But if you do want to create a subroutine to use in here, the world.jump method is the way to do it. However, if you want to make things easier on yourself for the homework, just use the built-in methods. Just drag it here and use the built-in methods instead of making a method of your own. So what I'm going to do now, show you the other one. The other list loop is for all together. So exactly the same code. World.jump, where the jumper is the item from jumpers. And this time they all jump at the same time. And so why do they jump at the same time? Well, because in this case, it's exactly the same as the for all in order loop, except that it executes the loop for each item in the list all simultaneously. So pretty easy to understand. It's exactly the same thing as the for all in order loop, except instead of happening one at a time, it all happens together. Exactly the same things happen, but in the for all together loop, they all happen at the same time. So they all jump at the same time. And my example here, instead of using the jump method I just said, item from jumpers move up 5 meters, move down 5 meters. Now here's an example of doing it wrong. Don't do this. Wrong. We have our jumpers. For all jumpers, one item from jumpers at a time. White rabbit move up, white rabbit move down, Cheshire cat move up, Cheshire cat move down, Alice move up, Alice move down. Or white rabbit.jump, Cheshire cat.jump, Alice.jump. Why is this wrong? Because you're referring to the items in the list by name inside of the loop. The point of this loop is you have the list up here, and you go through, and whatever's in the list, you make it jump. Here, you're not doing that. You're not using this item from jumpers parameter variable. You're not using the item from jumpers variable. You're saying white rabbit, Cheshire cat, and Alice. If this list changes, if you later add an astronaut to the list of jumpers, this code isn't going to work anymore because it's not making the item from jumpers jump. It's making all this stuff jump, which happens to be the same as the jumpers list, but it doesn't have to be. So this is very wrong. And if you don't understand why, it's important that you don't do this on the homework because it's wrong. It's also important that you understand why this is wrong. The list is providing you a way to do something generically. For anything in the list, you do this. For anything in the list, you do this stuff. You make it move up and you make it move down. So you can take the list and add stuff to it later. This is an example of how to organize code well. You're isolating the things that jump into this list. And so in this code, you don't worry about exactly what has to jump. You just take the item from the jumpers and, well, the programmer worried about what to make jump earlier, so I don't have to worry about it here. Separation of concerns. Compartmentalizing code so that some stuff is over here and then this stuff over here doesn't have to worry about it. In a program as small as this, it doesn't really matter. But that's the principle of the thing. That's the principle of why you would use a loop like this. And because that's why you would use a loop like this, the correct way to use a loop like this is like this, and not like this. So you're going to be making goldfish move. And in your code to make the goldfish move, make sure you do not refer to the goldfish by name. You're going to have to give the goldfish names. Then you're going to add the goldfish to this list. And then you're going to have two loops. Probably one where they move one at a time, or I don't know exactly what your loops are going to be like, but you're going to make a shark come, and then you're going to make them move together as a school. So they're all going to move simultaneously. So you're probably going to use the not one at a time. You're going to use every item from school together, and you're going to make them move as a school. And so you shouldn't not be referring to individual goldfish inside of the loop that you use to make them move as a school. Then you're going to make a shark come. Well, there's only one shark, so that doesn't involve lists at all. And then you're going to make the goldfish scatter. And how to make them scatter? Well, you have to make them scatter in different directions. So there are ways to make them scatter, and I might give you some more hints on this homework in an email or something like that, but this is all I want to go into for now. So remember, don't do this. Alright, that is the end of the last lecture. I will be posting instructions on the final project along with the final homework. And I look forward to seeing what final projects you come up with. You have a lot of creative freedom with the final projects, so I encourage you to make use of it. At the same time, I'm not going to be grading extremely harshly on the final projects as far as creativity, or I'm not going to be grading at all for creativity. I'm going to post the rubric for the final project, and I'm going to grade on exactly that. So it doesn't have to be original. I mean, it has to be your own work, but it doesn't have to be creatively original or anything like that. Just worry about the technical requirements. Alright, I hope you've enjoyed taking this class. I hope you enjoy the final project and this final homework. And good luck to each of you in all of your future endeavors. Goodbye.